is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Well, hello there, and welcome to Skytour Livestream. It is, who am I? I think I'm Mark. Yeah, I am. Nice to see you guys. I'm also here, of course, with Daryl Mason. You know Daryl, right? Do we know you, Daryl?
Not as well as... No, I'm not going to say that.
Yeah, okay.
Yeah, you know me.
Yeah, we know each other.
Hello, everybody.
Nice to see you all. Thank you for coming. Here we got this beautiful first quarter moon sitting right in our view here. Let me just acquaint people with the actual size of our field, okay? This is the whole field right here. You can see it. And so we basically have about 3 full moons across and 2 and slightly more full moons tall. So we're like 1.5 degrees, the 3 full moons by 2. So, 1.5 degrees by 1 degree tall. So, and we have more pixels, a camera with higher resolution, so we get to see more detail. So when we zoom in, on our moon. This is the live view. You can see that the image is a little better than we expect. And I'm going to try and... There is a way to just capture one single frame, and I want to do that. And I'm trying to remember how to do this. I'll just capture 100 frames. And what we can do afterwards is stack all those frames, but we'll do that offline because we're doing this at 1.95 milliseconds, so most likely those are going to be done here momentarily. So we've got 15 frames already captured, and so we can stop the capture, and so we have our capture there. All right, this is for Izabela because I know Izabela likes to see our captures of the moon, so I did this for her. So there you go. All right, let's see. So tonight we're gonna check out the star that we call the Blaze star. That's the Corona Borealis. Corona Borealis. It's a star that goes nova every 80 years, and it's actually primed for another nova event. So we'll capture it when it does go. Most likely we'll see it after it goes, unless we're watching it live, like we're watching the moon right now. Because we're watching the moon live right now, and if there was a meteor to strike the moon, we'd see it live, you know, just like we did for that eclipse. Yeah.
Hard to believe that was over 4 years ago.
I know. Shh, don't say. That was 2019.
Yep. Earlier in the year, I believe.
Yeah. All right. Hello, Renee. Hello, Jeremy B. Hello to... let's see who else is here so far. Karen Belmont, hi, how are you? Prow's with us, nice to see you. Prow. Trish Ferreira, hi Trish, how are you? And Mr. Michael Hedrick, yes indeed. All right, so we are here to check out the night sky tonight. It's not quite fully dark out there, but it's getting there. Let's see what happens if I live stack the moon right here. It's probably not going to work too well because it's too bright. I'd have to change the settings here. And that's possible to do. And you see it's blurry because we're stacking the moon, and we want to stack the moon before we actually see it's making edges. We want to stack the moon using a different technique because the software is not aligning the moon. It aligns stars much better. I wanted to also mention that Michael Hedrick captured this really cool Sundog, which is a ring around the sun with a rainbow. It looks like a rainbow around the sun. And the rainbow is 22.5 degrees or so, 22 degrees away from the sun on each side. And that happens to be the angle where the refraction in the ice crystals and that thin cloud layer above will break up the light of the sun and angle them down to your vision from that particular location. So ice crystals do a lot of really cool things. They generate ice pillars, which you can see in the sky sometimes when it's snowy nights or whatever, and you have ice in the sky. Northern latitudes get that a lot. You see pillars going from the sky all the way down to the ground. That's misleading. They're not really straight pillars going up into the sky. They're actually angled along the line of sight, and they are different for everybody who's watching. If you stand 100 feet away, you see a different ice pillar than you do when you're standing at one other particular location. So, I'd have to make drawings to show you how that works, but I'd be happy to if we do that at some point. Judy M is with us. Hi, Judy. Nice to see you as well. Okay, so let's go into our planetarium view here, because we're here right now on the moon. Okay, And we're going to,
Sky clock event.
yes, deep sky clock event. You probably can hear that. The telescope talks. We're going to go to the Blaze star right here and check it out because that's someplace we want to check out right away just in case something magical has happened. And we will set our time to 1 second. You'll watch the telescope moving over my head here. There it is right there. You see it pointing off there. It's going up north and pointing to Corona Borealis. And let's do this. All right. All right. We still have some blue in the sky right now, and that's because it's not quite dark. But while we're here, why don't we do an annotation and figure out which star in here is the Blaze star. I think it might be this one. That's my guess. So I'll leave my cursor there just in case. I don't think it's that one, but I think it's this one. Let's see here. Oh, it's up there. Look at that. It's way up top. All right. My mistake. All right, so what I'll do is I will bring it back down. All right, let's do that. Oh, there it is. And I guess that's it right there. It wasn't dark enough, so I didn't really catch the brightness. No worries. We'll do it now. What we can say for sure is that the nova has not occurred yet. Okay, let's annotate and make sure. It's going to say the old location, and we'll resolve. This, what we're doing is called a plate solve. It takes the stars in the view, and it analyzes tens of thousands of stellar positions, and it identifies exactly where we're looking in the sky. Okay, so right there is our Blaze star, all right, and then right near it, we have IC 4587, which is a galaxy. All right, and then we have a few other stars that are, well, there's another galaxy in here too, and I'm not seeing, it could be behind this. Yeah. Oh, the field has got some more extent. All right, well, it's saying that there's another couple galaxies in the view with us, but I don't see them at the moment, so maybe they're over here. Oh, okay, yeah. No. All right, well, I don't know. No worries. Anyway, so there's our Blaze star. That's the nova that's going to occur, the nova star. And it's known as also T, as in Tom, Corona Borealis. That's the designation of the star in Corona.
Can you open Stellarium again for just a moment?
Sure I can. Let me just get rid of this for a minute. Hello to Roni Hassan. How you doing? Nice to see you. Eliza's with us. Thank you. I'm glad you just joined. If you could, please subscribe. We'd love to have you with us.
Can you zoom in just a little bit on the Corona Borealis?
Yeah, I'm doing it. There we go.
Okay, that's a good scale there.
I'll try to right back out. Let me
All right, you see that curve of stars? That's the northern crown, Corona Borealis. Alphecca, the third star on the right, is the brightest star in Corona Borealis, sometimes called Gemma. It represents the jewel in the crown. And then if you go around to the lower side, the left side, T Corona Borealis is very close there to the second star on the left.
Straight on till morning.
Yep.
Second star on the left, straight on till morning. So yeah, this is where we are right here, and it's right near this star, and this star here is known as, looks like Sigma. Oh, it's Epsilon. Epsilon Corona Borealis. This is Delta. I couldn't see the Epsilon there in the wording. But our blaze star is in the middle of this, and if we zoom in, this red box represents the field of view of our telescope. You notice it's on the side here, so you have to turn your head to the left to see the field. So if the star is in the center, you'll see we have this star here, which is this star here. Okay. Then we have a star here and a star there. So if we come in here, all right, we have these stars. All right. And I think, let me go back to our value here. There's the blaze star. And so we have those two stars, and we have that bright star. Okay. And if we come into our planetarium again, you see those two stars, and we see that star. So 1, 2, 3, and then 1, where is it? 2, 3. So 1, 2, 3. So we have those stars in our view here.
Karen Belmont asked, how do we know something so far out, I assume she means, is going nova or went nova? Karen, they track such things. They have a record of the blaze star being a recurrent nova. Happens over and over again. And in the past, it has happened with about an 80-year period. During previous novas, they have noted the star's behavior in the days and months leading up to the nova, that it dims a bit, if I remember correctly, what I read. And I think when they saw that dimming this time around, gives them a clue as to how soon the nova is going to happen. They've been saying sometime between now and September. So at any rate, them watching the star has given them clues to its behavior, and if it behaves as it has in the past, well, they think it's going to happen between now and November.
And keep in mind that it's 2,695 roughly light years away. So when it happened 2,600 plus years ago when we see it. Okay, because that's how long the train of light is coming to us from this star right here. Now, you might say, well, how in the world can we tell what that little point of light's got going around it? Well, there's two ways, okay? Number one, by looking at the star's spectrum, we can see that there's, well, I'll tell you what I mean by two ways in a sec. We can see that there's a spectrum that also includes the spectrum of a second star polluting the first. Now, they orbit each other. So when the star's spectrum is for just the red giant, which is the one we're looking at here, then we see the red giant expected red spectrum. But when the white dwarf comes into view, we see other stuff in the spectrum. Now, white dwarfs typically are carbon oxygen surfaces, and so we would see lines in the spectrum that suddenly start showing up in the star's spectrum, and that's how we know there's an orbiting star around it. Okay, if we just see red giant lines plus these other lines that are in white dwarfs that we know of, then we know that the orbit's kind of going like this. So in other words, it never goes behind the star from our point of view. It literally is kind of going around the star in a way that we always see the white dwarf. So that's two ways we can actually identify the spectrum of a white dwarf pretty definitively. And knowing that they're closely orbiting and figuring out the orbital speed and closeness and proximity to each other, which we can also calculate, and that's a different talk, then we can figure out that the white dwarf is close enough to receive hydrogen gas through the common center of rotation, because the red giant used to be a normal sized star, right, like this, and then it grew massively and filled an envelope that's called its Roche envelope, and then it would feed through the center of rotation. It would feed hydrogen gas that might have leaked off the surface of the star that would land on the white dwarf. And then when a certain amount builds up, it could spontaneously go into fusion, this runaway fusion that happens on the surface of the star. And if the surface of the star receives enough mass, that'll happen. And if that mass is less than the special number called the Chandrasekhar limit, which is 1.44 solar masses, then the star will not blow up and become a supernova. It'll just runaway fusion will cause a severe brightening of the star for a period of time, and then from there, that star will then fuse all that hydrogen, and then over a period of a few days to a week, go back to normal brightness again.
And when we see the star go nova, it is in effect you're seeing a great big huge thermonuclear reaction, an H-bomb, in other words,
on the surface of the white dwarf, but not on
Right.
just one location, on the entire surface, because the hydrogen would be leaking onto the surface, and it starts getting distributed on the surface by the white dwarf's massive gravity. So it forms a thin layer, but at a certain point, it reaches a critical thickness, and so the underlying hydrogen is going to get hotter and hotter and hotter. And if it reaches a special temperature of around 15 million Celsius, it will then go into spontaneous fusion. And as long as the overall mass is less than that special number I mentioned, then the white dwarf will survive. It'll just go boof, make a big flash that'll last maybe a week or so, maybe a little more, and then tone back down, and then we wait another 80 years for the buildup to occur all over again. And that's just that's a transient phenomenon, because the red giant is also going to shrink down to a white dwarf, and then you'll have these two white dwarfs going around each other, and we'll never see that again. So it's actually a very interesting situation. And if for some reason the star is close to 1.44 solar masses, then there might be an end of life for the red giant, where it sheds lots of mass off of its surface and puts lots of mass onto the white dwarf. So it's technically feasible that although it may not reach that special 1.44 solar masses now, that it might tip the scale over that line should it start doing lots of mass ejection like some of these red giants do. And if it does that, then the blaze star and the companion star, that white dwarf, will in fact exceed that 1.44 solar masses, and that is too much for the star, the white dwarf star, to take, and it will then explode in what's called a Type 1a supernova. And that's, this has been doing this every 80 years like clockwork, so it's interesting to watch it and see what could be going on. This is our blaze star right there. It's also, you see, it says HIP, 78322. That's Hipparchus. Hipparchus is the name of the star catalog, and this is Hipparchus star 78,322. How romantic a name, I know. But blaze star sounds cool. All right, let's see if we can see a little bit of a darker. This is 1 second. Let's drop this exposure a little bit. The moon is out, so it adds this blue haze into our view a little bit. It's actually not that far from this. Yeah, see, Hipparchus disappears when you get down to these low numbers. All right, so we'll bring it back. Yeah, there we are. So, I see people asking questions. Daryl, you want it?
I think I just answered it.
Okay.
Izabela's here.
Hey, Izabela. Good morning. Izabela, as you know, is in Bulgaria. I think she's the farthest east person that we have. Oh no, that's not true. Australia. If you kind of keep going that way, they're a day ahead. So that would be some of our Australian friends. Yeah, very cool. I'm going to just get rid of this for a minute. And then bring it back. Yeah. Okay, we'll do we're going to do a capture on this as well. I'm going to call it T Cor Bor, and that's how it will appear on our, I'll call it Blaze Star as well. Oh, hey Hunter, how are you? Welcome home. Yeah, so that's pretty cool. So we'll do a stack on this, and I'll take it into about let's try 5 seconds and see what it gives us. Now let's get it into the stack here and move this out of the way, drop this down. All right, and do this. Yeah. Zoom our view. We'll fix this noise in just a minute. Okay, we're going to go like this. Pull this down. Pull this mid-range down. Excuse me. And now you can see that the Blaze Star has been selected. And I'm going to do a color correction there. And let's move the black level just past the peak to darken this a little more. All right. All right. And then we'll get rid of the labeling for now. Okay. And the annotation results. Well. All right, so, well, all right, annotation, we're going to save it with the annotation. Annotations are just the labels. And that's been saved, so now we have that out there. Okay, this is our Blaze Star right here.
You can see it looks quite red now.
Yeah, the red giant is really dominant, right? Because the white dwarf adds a little blue to it because they're spectroscopic binaries, meaning that you can only tell they're binaries by the spectra being of 2 stars. And Fantasy, how you doing? Nice to see you. Okay. Cosmic Rays here. Ray, we'll keep politics out of this, please. We're scientists, not politicians. Okay. All right. All right. So we did 25 of these, and we will save them like this. And we'll maybe check it out a little bit. Oh, you know what? We should check out the comet, don't you think?
Sure.
All right. Can you go to Sky Live and get me the coordinates?
Stand by.
Thanks. once again, there's our blaze star, the star that's going to go nova inside the crosshairs. It's a nova watch.
Current right ascension of the comet,
11 hours and something.
11 hours, 37 minutes, 43 seconds.
Okay.
Declination,
Yeah.
plus 03 degrees, 0 minutes, 24 seconds.
Okay. All right. Well, that's cool. So we'll just make one last save here of this. And then head over to that location for the comet.
It appears that the comet is now leaving Virgo.
All right. I do one thing while I'm here. I am going to zoom out again. And this comes from having done this the other night. All right, do this. There it is. I'm going to get out of this, go back to my 1 second low light shot. For reasons I'll make clear in a second. All right, and here we are. There's the blaze star right there. For proof, all you gotta do is bring up our annotation. There you see it. There goes a Starlink satellite. Okay, so here it is, and what I'm going to do is I'm going to bring it up to the crosshairs, and then I'm going to synchronize the telescope on it. I was using our new scope yesterday in a test. It's only sitting in our SkyTour Mesa office, and I wanted to show it to you, but Marianne and Dave Rich were on with Clyde Lewis tonight. In fact, they're on right now with him. So they had to unplug the telescope, which is fine because it's just there for testing. But for those that are interested, we're actually using a German equatorial mount system. We bought 2 of them. One for the Sonoran scope, this one we're seeing here, and one for the Benson, Arizona telescope. And that telescope is going to be outfitted with this system, and it's also going to have the what we call the Green Swamp server. All right, so let's back out of this now. There's the blaze star, and we're going to align with this star. There we go. All right, so now when we come back in, all right, now that we're aligned, when we go to the comet, it should be close to the center, but we'll find out. So let's say go to. All right, off we go. See, the telescope is shifting as we speak. Again, moonlight is adding a little blue haze to our view. Oh, we're close to the moon with this one. Or I think we just zipped by the moon. We just swung by it.
Deep sky clock event closing.
All right. Yeah, the comet isn't visible yet. Well, it probably is visible. I just can't see it yet. Let's just do a quick exposure and see if it's in the field. We'll do 10 seconds. All right. And we'll stack that. Get out of our low light view.
Your gain is 0.
Oh, well, that'll help if I... That's right, because I was... Okay. Let's do 150. Let's see where the moon is. I'm sorry. I'm going to drop us at 25. Yeah, it's dead center, I think. let's check that for sure. Let's go here. Let me do some calibrating, color correcting, and then do this. Oh, I don't see it.
Me either. Let me double check.
Well, hang on. Let me look down here below. It might be down below. Yeah, I don't see it. You said 11:37:43 and 03:024.
Yes.
Interesting. Okay. Okay. Well, I got an idea. This is a 10-second shot. Let's solve for where it thinks we are. So we're going to plate solve for where we think we are here. And that will tell us. It's got 100 stars to choose from. This should be pretty quick. I already found it. Alright. How far off are we? Let's find out. Alright, hold on a sec. Let's just figure it out now. Alright, we're at 11:35:19 and 3:37:14. So I guess if we go south, we should back into it. Let's try that. Oh shoot, I gotta get us back to our low light shot. And we'll get out of the stack. Alright, let's do this.
Here
There it is, right there. Okay. Alright, so I had to back into it. Alrighty. Alright, so this is Comet C/2023 Tsuchinshan-ATLAS. Okay, let's center you up. Alright, good. Come back here. Let's see how far off it thinks we are. Let's go to where it is sitting. Alright. Yeah, see how close to the moon it is?
Yeah.
It's pretty close. Alright. Alright. So, very nice. Okay. So let's now do a 10-second exposure here and see if we can get rid of the moonlight that will be very, very much infecting us. Okay, let's clear that. That's the previous attempt. Let's see what we got. Oh, there we go. So let's line up the colors and let's now do a basic drop this down. Climb our black curve a little bit. This is a perfect example tonight, guys, of looking at what happens when the moonlight, even though our filters work for us, the moonlight is now blending with the faint light of the comet's tail. And the other night, we actually saw much more of the tail here. Now, I'm only doing a 10-second shot, too, so if I did a little longer, we might see more. But if we punch this up, we can actually see what might be in there, but it's going to be really bright. So you can see that we're not seeing a lot of the tail right here. And that's only because the moonlight is blending with the tail light, and it's not allowing us to see the fainter light of the tail. Not bad, though. I will keep working on this to get it. We've got 7 exposures in here at 10 seconds already. So this is C 2023 Tsuchinshan-ATLAS, all caps. There we go. Not bad. Not bad for a moonlit night. Kind of fun for a moonlit night, actually. Seeing a relatively faint comet right near the moon through the wonderful courtesy of our really cool filters that we're using. Okay. I see we have Sam S with us. Hey, Sam, how are you? Donald Kunzer's with us. Hi, Donald. I saw you up there. Jeff Penn is here. Hi, Jeff. Nice to have you with us. Make sure you subscribe. It's all free. And click the bell and drop the little box down and say all notifications. So you'll get our notifications that we are streaming.
Michael H. has a question. Do comets or meteors or asteroids ever collide with each other? Yes, they do. Asteroids in particular. When you have little asteroids come from big asteroids because they ran into each other in the past and they fractured and broke off into little asteroids. Comets are more rare. I'm sure, over the history of the solar system, they've run into each other.
Mm-hmm. I think that's true.
We've said before, too, that a lot of people have a misunderstanding of asteroids because they've been watching too many Star Wars movies or Star Trek. You could go out in the middle of the asteroid belt and look around and you wouldn't see a thing.
That's right.
You wouldn't. It's not like the sky is literally filled with tumbling boulders. It's not like that. If you take all the asteroids and put them together,
I was just going to say that, yeah.
They would just make a fraction of the mass of the moon.
A fourth, actually. A quarter of the mass of the moon. That's a very low number, low mass, considering all the asteroids that are out there. So you can see that there's a lot of really small ones out there. And they're very, very far apart. Hey, Bonnie. Bonnie's here. She's not just lurking. She actually left a message.
Bonnie. Hello, Bonnie.
Yuffie Hattori is with us. And Vincent's Virtues. How you doing? Yes, this is the Tsuchinshan Comet 2023. Atlas. Indeed. Yep. Okay, we're letting this one build up. So far we have 25 exposures. Now I'm going to save it because it's moved in that time and we want a nice sharp nucleus. Alright, so what I'm going to do now is I'm going to make a 25-second shot of this, which is 25,000 milliseconds. Okay, and we'll clear this. The exposure is underway. Oh, it didn't do it. Okay, let's do it here. I don't know why I said 25,000. Okay, here we go. You see our little progress bar over here, right here in the yellow? Yeah. Yeah, this guy right here. This progress bar tells us the extent of the exposure, where it's going. You watch it travel across, that gives you everything you need to know. Alright. And, boy, that took a lot of energy going all the way across the screen. Alright, let's see what we get now. We got this exposure work.
Michael, you probably wouldn't see anything if and when they collide asteroids, unless you're looking right at where they're going to hit. If you saw that mission, I forget what it's called offhand, where they flew a spacecraft to crash into an asteroid that was orbiting another asteroid.
That was DART, and that was Dimorphos and Didymus.
Thank you. It made quite a mess when the spacecraft ran into the smaller asteroid.
It did.
But if two asteroids collide, it's not like you're going to see a explosion or a flash of light or anything.
No.
And if they weren't looking right at it when that collision happened, they never would have seen it. Mark, excuse me a moment, please.
Yeah.
Right back.
Sure. Okay, why did the comet not show up with a 25-second exposure? Let's go check out the all-sky. Oh. Well, look at that. We got some light clouds passing through right now. That explains it. There's some right here. This is a reflection, actually, right here. Okay. Interesting. Let's try moving this here. Yeah, we're getting some clouds in here. How about that? Okay, well, we'll have to come back to this region of the sky. Right now, let's try something else. Let's come over here, all the way to the opposite side of the sky, and let's check out something else that's nearby. It's going to be up higher here. That's what we want right there. That should be out in the open. Okay, we'll center up on that. And let's go. Telescope's going to swing all the way to the opposite side of the sky here. There it goes. You can see it doing that right now. Heading up and away. Sometimes the winds that we have out there will cause the not the winds, but the cloud systems will come up pretty quickly as the desert cools. Let's do this. There it is. So it's in the clear. All right. So let's zoom in on this a little bit. Okay. So this is Measure 13. It is the Great Cluster in Hercules. It's a globular cluster. Measure 13. The GC, a globular cluster. All right. So now what we'll do is we will go to 15 seconds.
Oh.
Yeah. We had a issue out there. There were clouds. Some light clouds passed over the comet and completely did this to us. So we got to get rid of them. So we're going to clear these here. Let's go back to the all sky so you can see what I was talking about. See that stuff? Yeah. This is a reflection. That is a little bit of a cloud bank right there. So we're going to get rid of that. All right.
Let's add the question of you.
Okay.
Right down at the bottom.
All right. Trisha, let me go look. If you're offered a seat to visit the space station, would you go? What do you think, Trisha? Yeah, I would, of course, go. I trust Elon Musk and the Dragon. So I'd go on Dragon. I wouldn't go on the Soyuz. I'd go on the Dragon. Sure, I would. I mean, just for fun, I would probably ride the Vomit Comet first, which is that aircraft out in Vegas and elsewhere where they do like 15 loops, like not loops, but parabolic curves, and as they do it in an old aircraft, and all the seats are removed and it's all padded, and as they go up, you're lying on the floor, and then you come over the top and you go weightless for about 15 seconds, and then you slowly come back down to the floor. They do that 15 times. If you lose your lunch on the first pass, you are stuck for 14 more times. So I just wouldn't eat. I would just probably not eat and have dry heaves the whole time. It'd be the most fun I had getting airsick, I can tell you that. That's beautiful. Look at that. Measure 13 looks really pretty tonight. I always like this orange star in the field.
Yeah.
Yep.
I see the propeller already.
That's right. The propeller is this right here, this line. And that's actually quite prominent right now. What you can do is actually highlight that pretty easily by doing this. Okay, my line is just to the right of it, and then to the bottom of it, and to the bottom of it. So you see those three lines, right? And I'll clear those now so you can see them. There they are. 1, 2, 3. It's what he's calling the propeller is just a visual artifact of the way the stars are laid out from our position of our viewing spot in the galaxy.
Can you zoom in a little?
Yeah, that's what I'm trying to do. I'm waiting to yeah. I'm waiting to get some control back here. Oh, no wonder. Duh. Sorry. Yeah, I can zoom in. Here we go. That's a little too much. But it is good.
You
can see it right
three
there.
dark lines show up rather well there. They're at about approximately 120 degree spacing.
Like an
three of them.
Yeah, like an equilateral triangle. If you draw a line between them, you get this perfect set of equal line segments. This is simply by chance. We see a lot of that out there. Fantasy goes, oh yeah, who doesn't love the Vomit Comet? Yeah, right. Prowl says he would do it. I would do it too. I really would. Trouble is, they only take like 15 or so people, and if you amortize the cost of a flight among 15 people, you're paying like $8,000 to $10,000 a person to ride on this thing. You know, I would like that. Well, Karen Belmont talks about G-forces. There is no G-force, though, on the Vomit Comet. In fact, it's lack of G-force. It goes over the top of the hill, and it's that feeling you get in your stomach when you go over the top of the roller coaster hill. Okay? There's no G-forces there. You actually have low G-forces. And what's funny is astronauts feel that way 24/7. They have to sleep like that. They have to go to the bathroom like that. They have to work like that. And it's not for everybody. You know, I remember there was one very wealthy dude that went up on the space shuttle, not the space shuttle, went up to the space station, I think from Soyuz. And when he did that, he got up there and he was sick the whole time, and he could not enjoy his $250,000 trip to the space station, or whatever it was. I think it was $250,000. So he did not enjoy it, and so I would consider that a waste of money. Okay, we'll save this.
I guess the sensation is literally you feel like you're falling 24/7,
Correct,
and
because you are.
some people get used to it, and some never do.
Yeah, I'd like to give it a shot, you know, because when you're falling, the first thing you want to do is to go, you know. But how long can you do that before you realize, okay, my body has to acclimate to this, you know? And if you know that the plane, for instance, is supposed to do that, or that that's how it's going to feel at main engine cutoff when you're riding up in a rocket into orbit, then you can expect it and say, ooh, I could learn to enjoy this maybe. But if you don't know it's supposed to happen, your adrenaline surges and you're thinking, what the heck's wrong? You know, is the plane falling out of the sky or something like that? I've been in a few flights where the plane dropped like 1,000 feet in a few seconds, and the trays and stuff and everything that was on your table, your iPads, your computers, shot up to the lights, and then banged the lights and came back down. I had to catch them, you know. And I found myself going, yeehaw, really loud too. And I guess that was a nervous reaction. But fact is, if you don't know what's supposed to happen, it's a lot worse than if you know what's going to happen, you know. And the other thing too is, like, some people say, oh, well, you go to those skydiving places, right, where you get inside the big fan and you float. Yeah, there's no weightlessness there. You're just being pushed by wind. You don't feel weightless. You don't feel like you're falling. You just feel wind going by you, but you're still subject to gravity. True weightlessness is when your organs and your blood flowing through your body is redistributing because there's zero G. The first thing that happens to astronauts when they get to orbit is their faces get fuller, and their face fills out more. And that's because there's more blood flow, and it's even for the first time in your life when you're in zero G. Gravity keeps, pumping the blood to your head, okay, and your heart doesn't know any different, so it's trying to pump that blood uphill to your head. But when you go to space, it's still doing that. So your head goes bloop, and some people get a big, thick head. They get, headaches and stuff like that. So they have to be ready for all that, And Prowse says, same sensation then when you're skydiving. You reach a terminal velocity, and it's while you're accelerating that you're feeling that sensation. So when you're reaching a terminal velocity when you're skydiving, that feeling of falling isn't the same as while you're accelerating in the fall. But in space, you're constantly accelerating. That's the thing. It's different than skydiving. Because as you're going around the Earth, you're falling with the spacecraft, but you happen to be going horizontally at just enough speed to stay in a circular orbit, but you're still falling. With a skydiving situation, you've got air, so you fall, you accelerate downward, you feel what astronauts feel, but then you reach a constant speed. And that's what they call terminal velocity. For humans, it's like between 120 and 180, depends on what you've got on and what you're wearing and stuff like that, I think. So it's pretty cool. I would think that when you reach terminal velocity and you just have your goggles on, the helmet and whatever, you could be lulled into complacency thinking you're just sort of staying there. Because at terminal velocity, it's like when you accelerate in a car, you're getting pressed into the seat, but when you reach the constant speed, you don't feel like you're moving anymore. So it's the same kind of thing. Astronauts, however, are always falling, always feeling that acceleration due to gravity like that. So that's my take on it. It's kind of a weird kind of a weird thing to experience, I would think. Okay, let's save this here. We got enough of these.
You want to see an example of bad science in the movies? If you ever watched that crummy Disney movie, The Black Hole,
Oh, yeah.
early on, the good guys fly in a spaceship before they land on the big ship. The ship's engines are running, and so they are accelerating. And then the camera cuts to the inside, and they're still weightless. They're floating around,
Yeah.
which wouldn't happen. I mean, if you're in a spaceship and you fire the engines, well, you're no longer weightless. You're going to move toward the back of the spacecraft or wherever the engine is.
Technically, you're right, and I think, and I agree with you that's just overlooking science. But I will say this: if the acceleration was a small acceleration, then they would float to the floor, and they could simulate, for instance, a third of the Earth's gravity, or a fifth of the gravity, or a tenth of the Earth's gravity. But they would have to be doing a very slow acceleration for that to be the case. And when they jumped off the floor, they would float for a while and then come back down to the floor. If they're accelerating at 1g, 1 times the force of gravity, then yeah, they jump up and down just like we do on the Earth. But the black hole negated all of that and didn't even consider it. Yeah, they should have been slowly coming down to the deck at the very least. All right, want to do 4725? Can we do that, you think?
Sure.
Should we do want to do Measure 92 first?
You like, sure.
All right, let's go there. That's another globular cluster, but let's get a last look here. This is Measure 13. Let's look at one that's also often looked at. That's Measure 92. Okay. Now, when we look at Measure 13, all right, we're looking at a globular that's 25,000 light years away. So you're seeing its light as it was 25,000 years ago. Measure 92, on the other hand, is 26,000 light years away. So it's slightly further away. And so let's check out what it looks like as opposed to this. So I told it to go, and we should see it heading off to do it right now.
When they had Arecibo send that message out into space.
That was called the Arecibo message, correct?
Yeah. I read they aimed at it Messier 13.
They did.
Which is, in hindsight, that's a really poor target.
Yeah, because
A, it's far away, and B, those are all top 2 stars.
Which means early stars.
Low metallicity and highly unlikely to have any kind of life in the cluster.
That's exactly right. We've been saying that for a long time, Daryl and I. And that is that when you look at stars that are in the globular cluster, these are among the oldest stars in the universe. So I think when the Arecibo message was sent, I think it was in 1975 that was sent.
Something like that.
That message was beamed at the globular cluster, and it really didn't make any sense to send it to the globular cluster, as Daryl just pointed out. And when he says low metallicity, what it means is there's not a lot of elements and chemical abundance in the stars, and any gas and dust and there's very little dust in these globular clusters to actually make planets. So it was probably aiming at literally a dead spot in the universe. It would have done better to aim toward the center of the galaxy, as a matter of fact. It'd be about the same distance, and it would actually stand a higher chance of impacting a place that might have had life in it. Okay, we're going to do a 20-second shot here. 20,000 milliseconds, that's it right there. And we're going to get out of low light mode and jump into our stack. You can see our nice progress bars going. So this is Measure 13 with an interloper. All right. And beautiful red giant, most likely.
When you see M13, that's the second best globular in the sky, I think, or second or third.
It is.
Omega Centauri and what is it, 30 Doradus
Yeah.
are bigger,
Well,
but they're far south. We can't see them from here.
but we'll see them when we have the telescope set up in Benson. Omega
Yeah.
Centauri, anyway.
When we see Messier 92 here, it's quite different than Messier 13.
Yeah, and it's only 1,000 light years further away, apparently. So you can see here that it looks smaller than Messier 13. So Messier 13, the globular clusters aren't all the same exact size. Some can have hundreds of thousands, if not, a million stars in them, and some have 30,000, 50,000, 150,000 stars. Still, that's no small number of stars.
If you ever see Omega Centauri, it's like 4 million stars,
It's this big in the frame.
and it's as big as the moon in the sky.
Yeah.
Visually, it's stunning to look at. Messier 13 is, I forget, hundreds of thousands of stars.
Yeah.
And then Messier 92 here has, it's just not as nice as, it's a nice globular, don't get me wrong, but it's not as big or bright or as many stars as Messier 13.
Sure. I will say this. This telescope, you notice in the building here, you see the walls, right? We may be moving this telescope down to the southeast Arizona for a slightly darker sky and to a different type of enclosure altogether. It might have the same enclosure type as the other one that we're setting up down in Benson, and that's a pop top. So you'll have full access to all the horizons. So we'll get to see with both telescopes, this one which is a wide field and this next one which is a narrow field. You'll get to see all these objects right to the horizon. But as astronomers, we never look toward the horizon except if we're doing visual stuff for YouTube, for people to entertain like we do. If you're doing research, that is something that you don't do, because that's too close to the horizon. You get too much interference from what's called air mass, the mass of the air between you and the stars. Because the further you look on the slant angle, you're looking through more atmosphere, and that greatly affects what you can see and the color and the data that you're getting from it.
Prow asked 4 million stars, question mark, I think, and looking it up here.
In what, 92?
No, in Omega Centauri.
Oh. Well, it's the closest
they say
globular to
in
us.
Wiki, approximately 10 million stars with a total mass of 4 million solar masses.
Take that, Prow. You're almost right. Well done. Yeah. And Omega Centauri is actually pretty close to us, right? What's the distance of it?
17,000 light years.
Yeah. We're looking at this one. It's 26,000. So imagine it being closer. I mean, it would be a lot bigger in our view. Cosmic Ray, boy, you're rough around the edges, aren't you? How many years to build the Benson site? Go away. I don't want to hear it. It's not your money that we're spending. Okay? So put that rough stuff away. I don't want to hear it anymore. You're really bothering me with that.
Oop,
That's all right.
sorry.
That's okay. So anyway, Messier 92 then is here. This looks really pretty. I'm going to keep it as well.
And where we saw the propeller in M13, I see a dark bar running from upper left down toward the bottom.
That one right there.
In this one, yeah. It looks
Yeah.
like a dark patch and a dark bar.
Yeah, let me... Yeah, thank you, Izabela. I'm going to resolve the core a little more by doing this. Okay, and once it clears up, You'll see that dark bar very clearly now. See it? And it's really not a dark bar. It's just an absence of stars in that particular look angle that we're looking at this point in Measure 92. Let's do it even further.
Contrast effect, something.
Yeah, it's because we don't have any gas and free dust in these things. I think I got to refocus too, as I can tell right here.
Okay, you see, it's bordered by a row of brighter stars on the left.
It's making an illusion. I'm gonna take us out of this for a minute and go do a refocus.
It is a much sparser nebula than or cluster than M13 is.
You said nebula. No. Yeah, you're right.
Sorry.
Now, who cares? You said right. That's right. Okay, so there we are. So what I'm going to do is I'm going to drop this down and get us to a point where we can do the focus again. Fantasy, you're funny. That's all right, guys. You know what? Ray is a good guy. He just flies off the handle sometimes. So I just gave him a little warning, and Izabela gave him a second one. That's good. All right, so now we've got 9 stars down here, now 12. As it gets more in focus, that number is going to climb, now 30. And you don't see them because they're in the field, but you don't see them. We have to back out for you to see all the stars being selected. See that? And these are building a curve, a focus curve, and that center of the focus curve is the interpolated center. It's not the exact center, as defined by the units it takes to go to them, the divisions. If we put, right now I have 12 steps. It does 12 focus positions and then interprets where the best focus is. If I was doing research, I'd probably have 25 divisions to get exceedingly sharp focus. So you'll see right here, about here, you're going to see a line show up. Okay, right about there, and that'll be the focus point. And that'll happen any second now. Right around now, we're at 8, 9. Let's see. That's a very nice curve. It's probably going to show up right here. There it is. Okay, so now if I just let that go, it'll automatically go. But I tend to say, well, let's just go for it because you guys are waiting. All right. So out it goes, and back it comes, and now we have focus. So you notice it's not, these are the discrete motions that the focuser took. 1, 2, 3, 4, 5, 6, 7, 8. I let it go to 9, all right? But the thing was, it kind of interprets where the lowest point in the curve is. So you get a better detection or assignment of that lowest point if you have more curve points to interpret from. But I've found that 12 is more than enough. All right, and let's go 20 seconds on this because 25 was too high. All right, we're going to come out of low light mode and go back into our live stack, and then we'll be able to zoom in. You'll see crystal clear pointy stars. These are soft focus right there. We want a sharper focus. Fantasy says, that curve looked like my stock portfolio. That's funny, man. I think. Okay, so now if we zoom in on Measure 92, we should see some really well-focused points of light in here. Yeah, okay, so we have some noise, of course. Let's do this, and let's this white curve is our average of the red, green, and blue curves that make up our image. So if you go just to the left at the top and then drag this middle one out, you'll get rid of noise as best you can. There's another thing I could do for noise reduction, and this is a good magnification to do it with. See all the colored modeling in here? Watch this. click this, and boom, look at that. Instantly better shot. And that has to do with removing color noise generated by the camera. And there's Daryl's dark bar right here.
Yeah, more like a bright line of stars.
Yeah, like this here. These are the bright stars. And on this side, there's a couple that seem to define it. Yeah.
This Marc said, I think, when we look at globular clusters, they're among the oldest objects in the universe, which means they formed the earliest. Globular clusters, you might be talking 11,
12 even, yeah.
13 billion years old now. And other galaxies have them. If not all, most do, I suppose. I know when we look at Andromeda, 10S telescope may not show them well, but Andromeda galaxy M31 actually has many, many more globular clusters than Earth than the Milky Way does.
Yeah, it does. That's exactly right. Yeah.
What are they? They may have been the initial seeds of like star formation. They may have become the cores of early galaxies.
Yep.
Who knows? And some of the ones around our Milky Way may be what's left of satellite galaxies that the Milky Way sort of absorbed a lot of their stars.
Yeah. These are known as halo objects. They orbit the galaxy as a whole, but the galaxy is a big disk, so they will plunge through the disk and then down, then come up through the disk. And as they do, they may, and I don't know, I have to research this. I still haven't. Shame on me. They may shed stars doing so or gain stars doing so. I haven't researched that yet, and I haven't looked into that, but I would imagine it's very possible.
Say that again?
As the halo objects, which are globular clusters, and the ones that are closer to us, they will plunge through the galactic disk and then plunge back up through the galactic disk as they orbit. I imagine that that's true, and I imagine that they will also shed and gain stars in some way as they do that.
Oh, yeah. I think we've talked about this before. When we look at Messier 4 Globular Cluster in Scorpius, it's just to the west of Antares. That's the closest globular to Earth, and its distance is short enough, and its location in the sky is, it pretty much has to be inside the disk of the galaxy right now.
As it is, yeah. Michael Hedrick, you're asking a question about seeing if we could see positional difference by one side of the Earth's orbit or the other. The answer is no. That would be parallax. Parallax works out to about 300 light years. And that's the shift you see when you hold your finger at arm's length and you close one eye, then the other, and you watch your finger shift against the background. In astronomical terms, your finger would be nearby stars, the wall would be more distant stars, and your eyes represent one side of the Earth's orbit and the other side of the Earth's orbit. So when you do that, and you blink left and right, you watch your finger shift. I worked in that very program, actually, studying nearby stars when I was getting my degree in astronomy, and that was what's called the parallax program at Van Vleck Observatory. And that was that's good out to about 300 light years, but beyond that, we have to consult other methodologies in the cosmic distance ladder, including Cepheid variables, type 1a supernovae, and so forth. So there's a lot of interesting ways in which we calculate distance.
The satellites that are doing it now, Hipparcos, I think, and other ones, they are measuring parallax, but much more finely than we ever could from planet surface, right?
Yeah. And they give a better view, but we're still limited by the actual amount of distance that create that angle. Yeah. Yeah, Ray is also complaining about the fact that I haven't got the East Coast site up. As I said, it's not his money that we're spending. If it was his money we were spending, he might have something to say about it, but he doesn't. You know.
Working on a shoestring.
Well, yeah. We have Patreons that are helpful. They actually give us enough money to pay for the internet. And one of our benefactors is why we have the 11-inch Celestron scope and the 2 mounts. But, you know, we're working at it, trying to build it up. Izabela's done this phenomenal database tool that allows us to search for everything that we've done over the last several years. And for instance, we could look at every time we took pictures of M92 right at a glance with just minimal keystrokes. Things like that is really, really cool. Yeah. Thank you, Izabela. She put up that. Izabela is what I would call a super user of SkyTour. And Izabela, we got to get you to come on live again at some point, because I'd like you to tell people what you do, how you made the database, and I'd also like to have you explain from your perspective how you discovered asteroids in previous data. Obviously, I know how you did it, but I'd like to have you have the opportunity to tell everybody how you did it, because I think that that's a phenomenal research. That's phenomenal research that you did using our data. And you literally built the structure to do it. You built the database to do it. It's called the SkyTour Stargazer Companion, and we're making it available sooner than later. We already have it in testing. It'll be available on the PC, on the Mac, on Apple, and iPhone and Android. But we're getting there slowly.
Fantasy asked, do the clusters have a point they all rotate around like a black hole or something? The globulars around the Milky Way, I assume, are orbiting the center of mass of the Milky Way, the center of the galaxy, in other words.
Yeah.
And there's a supermassive black hole in the center. So I guess that's fair enough to say.
Well, these stars are also orbiting each other. And if there's a black hole in the center, I haven't seen research indicating that, and that could just be my failing. I mean, I don't know if there is. So I think that's pretty cool. Izabela says on this application, yes, I'm starting to send invitations for some testers. We'll figure it out for everybody soon. Yeah. Okay, so this is good. We have enough here, and we're going to save Mission 92 one more time and save exactly a scene. Here we go. And now we'll get out of that and go into our low light mode. Okay. There we are. Low light mode. Okay, let's go back out now to a slightly wider view. Okay, we'll go to 25%. All right, go into here, and I'd like to see if we can see this. I'm not sure we can. I want to find where 4725 is. Ooh, that's way up there, so we might be able to see that. This particular galaxy is a really cool galaxy. And Curtis Horn is the one that turned us on to this galaxy last time.
Yep.
And I want to see if we can check it out. It's almost directly overhead, so the imaging will be pretty spectacular if we can get it to show up. I'm not sure if this must be it right here.
Looks like.
So we're going to drop this down. Make the telescope head south a bit. Okay, and then we're going to head east a bit. There we go. Okay, and this is going to be a 25-second exposure. And
4725 was actually, when we first saw it the other night, actually it's pretty close to another galaxy we were looking at the time, wasn't it? I don't remember what it was now.
Yeah, I don't remember.
It was in Comet Varanasi, same part of the sky.
Yeah. Okay, when we start getting numbers here, we'll have been locked on with our guider, and it's right here, I believe. So it takes about 14 seconds, so we've just about got there. I'm waiting for it. Why isn't it coming in? Oh, I see where... Alright, well, I'll give it a shot. Do the live stack here. That is mesh 92. We're going to clear that. That's beautiful. Actually came out really nice. Alright, let's go see what happens here. There we go. Let's color correct and do this. Alright, and to move this over. We have several galaxies in this view. We'll annotate in just a minute. And we'll drop this down like that just to kind of get rid of the bulk of the noise. Okay. I know this says searching, but it's actually, it's guiding. So I'm not sure why it's doing that, but we'll find out.
Karen Belmont, if you can identify the bright star Arcturus in the constellation Bodes.
Yeah, I saw that. Let me see if we can just get there and show her. So you follow the tail of the Big
Corona
Dipper.
Borealis is
Yeah.
east or east-northeast of Arcturus.
Yeah, so this is Arcturus, and to find Arcturus, you look at the Big Dipper here, and you follow the tail down, and it points to Arcturus. Okay? And as Daryl just said, if you look up, you might see the kite stars of, this is we used to call it the kite in Bodes. And if you can't see the kite, then you look basically for the northern crown. You can actually see that. And then you look right around here. This is where it's going to be. It's going to be a new star in Corona Borealis for a short period of time. And that's pretty cool. Yes. All right. So, I'm going to darken our background a little bit, climb our dark curve here, our curve, and let it correct. And there you go. Now you can actually see this. Let me, if I color correct one more time, we should get a little better color here. With the moon getting brighter, it's going to be a little tough. But you can see here, we got several galaxies in here. Several galaxies, actually. So let me do this. We're going to back out, and I'm going to do an annotation to identify the galaxies we're seeing here, because that's cool. So let's do a sky annotation here. So it's now looking, and it will identify the different galaxies in here in just a moment. I love this feature. I think that was it's a beautiful, there we go. Beautiful feature. Beautiful, beautiful. So this is NGC 4747, NGC 4712, and NGC 4725. NGC stands for New General Catalog. Pretty cool. Okay. Michael Hedrick. What makes Jupiter's moon, no, that's Saturn's moon, Titan, have such a thick atmosphere? In the formation, it was just a lot of nitrogen in that particular region. So Titan formed with a lot of nitrogen. Some of it came from interactions with the crust, but most of it was the primordial atmosphere that Titan was actually formed with, Michael. And that's Saturn's moon, Titan, not Jupiter's moon.
Yeah, we straightened him out.
All right. You get your butt straightened out there,
Oh.
Mr. Hedrick?
Michael, Titan is the most massive of Saturn's moons, so it would seem kind of natural that it would probably draw the most gaseous
Yes,
elements.
yeah. Okay, NGC 4725, GAL for Galaxy. We will save the image with annotations, and then get rid of the annotations because we won't need them. So what you'll get out there, here's what's going up on the server, is this guy right here. You'll see this on the server. You can download it and check it out, use it for your own edification and research. All right, and now let's zoom in on this and try and grab some more detail out of this. Now that we've got 13 shots here, let's pull this in. If we move this toward the middle of the peak like I'm doing, we're getting more data involved, and it's going to bring out more detail in here. And as you can see, this has a long center bar in here. There's a nucleus, but then a small, a large bar. This is called a barred spiral, B-A-R-R-E-D, barred, like bars on a window. Barred spiral, and the spiral arms come off of that. Okay, same as on this side. They're a little bit different from each other, which means that maybe there was interaction between this galaxy and another nearby galaxy, possibly this one, or possibly a different one. Sometimes it's the galaxies you can't even see that are doing all the interactions. Let's actually push this a lot. So you can now see all this additional data in here. Okay. And if we actually use this other histogram over here on this side and push that up, just right up top, you'll see tons more data that's actually here. We won't actually use this, but we could bring this over here and start to utilize this data as well. But I'd rather not go to that second histogram if I didn't have to, because that actually adds noise that we don't really want to see as well. But this is beautiful, and this is the Galaxy NGC 4725. Now, I always say this, but think about this. What if you're looking at this galaxy, and what if, those of us watching the stream are looking at this galaxy right now? We could very potentially be the only people on Earth looking at this galaxy. So the light from that galaxy traveled however many millions of years to get here, okay, and that distance is around 67 million light years. So the light left this galaxy to reach your eyes right here, this instant, 2 million years before the dinosaurs died. Think about that. And then the dinosaurs died 65 million years ago, and the light was already 2 million years into its trip that you're seeing right now today. Let that blow your mind. I think that's pretty cool. And the universe is a giant time machine. I've always said that. You're not seeing the universe ever the way it is now. You're seeing it as it was, never as it is. But that's pretty. Look at that, huh? Not bad.
Yeah.
You can see.
We may be losing some fine detail to the moonlight.
Yeah, we will.
I can see hints of stuff going on.
Right there.
Both at about 5 o'clock and about 11 o'clock.
You mean this stuff here?
5 o'clock and 11 o'clock.
Okay, so you're talking about 11 o'clock up here.
Farther out.
You mean out here? Out there?
Right there.
Oh, yeah.
And there's hints of a dark band passing from about 9 o'clock down to 6 o'clock or so, maybe even 5 o'clock.
Like right
Farther
here?
down, outside the galaxy.
Oh, here?
Right there. You don't see that?
Yeah, I do. Yeah. Interesting.
And there's lots of... it looks like something has torqued the galaxy. I don't know about the galaxy to the right or what, but, gravitational interactions... something is definitely kind of misshapen the big galaxy.
Yeah, that's what I
4725.
that's what I said before. It's either, based on the difference in how this looks, it could be this galaxy or maybe another galaxy we don't even see. There's a lot of dwarf galaxies that have a significant effect on these galaxies.
Oh. Cool looking galaxy.
Yeah, I'm going to try and draw some differences out. Oh, go away. That's like a supernova. Okay, so let's go back to our color. There's our color corrected view.
Karen, I don't think we have much to worry about with gamma ray bursts. No stars. Current thinking is that they'd have to be within 200 or 300 light years to be able to affect us, and there are no stars capable of producing a gamma ray burst within that distance. Some, though, boy, you'd have to wonder about. There was that really big one.
Yeah.
They detected, I think, with Webb a while back. It was like billions of light years away.
It affected
Like
us.
the brightest thing ever seen or something. And if that had been anywhere within millions of light years of us, it probably could have fried us.
And there was one, it actually did affect us. It was a minor effect, but it did affect our...
Right, yeah. It had effects on the atmosphere. if I remember
Yeah,
correctly.
yeah. Okay. So these are here. We're going to save this guy. Tonight's another short and sweet stream because it's almost 1:30 a.m. here. And I do have to do some things tomorrow. And I
Me
will,
too.
yeah, so we will have to call it. But I did want to say that these will all be out on the server. See that look right there? That's what you get when you have a moon out, and we're doing a what's called a flat field correction. The flat field correction doesn't work. So what I could do, we could try, is removing this for nights where the moon is very bright. I will do that next time, just to see what we
Izabela
get.
has a question of you.
Okay.
Well, that's a neat red star, twin red star up there at about 10 o'clock.
Right here.
Yeah.
Yeah, that's cool. Might be a line of sight, but it could be. Yeah, Izabela is wants to hear about Ursa Major, the Great Bear. Yeah, I walked out my door. Well, it more than that, but the end result was after I chased him from my shop, he ran around the corner and grabbed garbage out of my bin, which he destroyed. So I went out the door and I was like, "I'm gonna slap your butt." That's not what I said to him. You know, how dare you grab my? You got no respect, man. And he was looking right at me, and he grabs the stuff and starts to walk away. And I said, "Oh yeah, where do you think you're going with that, you jerk?" And he had to be about 250 pounds.
I
And
saw the video. Did he growl at you?
yes, he growled and hissed. And you actually in the video there, the sound in the video, that's my dog growling at him. I did not let her out, but when he got over to the across the driveway where he started tearing open the bag of garbage that he got, he started going, at me when I was getting close. So I left Dingo in the house. I didn't let her out because I didn't want her. She will chase the bear into oblivion, and he's just hungry. So we get him all the time here. So at this point, I was working with the garage door open. My mistake. Okay, but I wanted to get some work done, and I had to keep going back and forth into the garage. So it was okay. I call him Barry. I always give him names. Barry was cute.
I want to think twice about leaving garbage outside too.
Well,
Trash bags.
he destroyed the bin, and so there was a bin. It was sealed up in the bin, but it was one of those Rubbermaid plastic bins, and so he just swiped at it and it broke it into parts, and so we got a contractor coming in to build us a heavy duty wooden bin with posts at the corners. So that was pretty cool. I gotta say, it was kind of interesting to see him a little, right literally 8 feet from me. It was kind of interesting. Oh, that's a good shot. Good thing I saved it. I'll save a new one here. But anyway, yeah, so that little Barry was there, 250 pounds worth of bear. His head was pretty good size. He's a pretty big bear. But the black bears tend to be very timid. The only time they're not timid is when they're very hungry or when they have cubs. So I was very cognizant of the fact that there were no cubs following this one around. But he had food. He had that bag, and so he was growling at me. You might say they have food aggression. So I would not be trying to say, "Give me that bag, you."
They say if you're attacked by a grizzly bear, lay down and curl up, play dead.
Yeah.
The bear's, trying to eliminate a threat or show dominance. If you get attacked by a black bear, fight back, because if it's in a mood to attack you, it's thinking of eating you, and you have to fight back or it will eat you.
Well, black bears are typically nut and berry bears, but if they get really hungry, everything's fair game, including dogs and cats.
Yeah.
My neighbor lost 2 chickens to a black bear, maybe the same one. Hey, D Cruiser, how you doing?
They've had a couple of instances here, a few in recent years of people getting killed and eaten by black bears here in Colorado.
Yeah.
Last one I remember was up in elderly lady in Ouray, Colorado, near Ouray, Colorado. Uh, she had been feeding the bears, and the authorities had told her to stop doing it. She kept doing it, and
Yeah, some people think that just because you feed them, they're going to be like dogs.
yeah,
Yeah, not true.
and one of them
You can't
got
trust.
hold of her and pulled her through a fence and
You can't trust these things.
had its way with her.
Yeah. D Cruiser, on my Facebook site, I have a video of the bear, the actual video of him with my garbage, and you hear all my commentary.
Yeah,
It's-
Izabela just posted the link.
Yeah, okay, thank you. Thanks, Izabela. Yeah, it's actually pretty humorous. You know, as he's running away with my garbage, I went, well, now I don't have to take it to the dump, thanks. You know, something like that. Don't gotta go to the dump now. But then I went out today and I cleaned it with watching an eye. You know, looking around. I was looking to make sure he wasn't around. Because I could see, I mean, he actually, for the winter, he bedded down behind the house here, up in our thicket behind my house. He climbs up a hill and it's all thicket up there. And he was in there all winter. And she's probably, if it's a female, it's cubless. It didn't have a cub or two. And if it's a male, it's small for a male. So I'm not sure. All right. Well, this is good. We got a number of them here. We're going to save one last time. And save exactly as seen. All right. Beautiful, 4725. Now, let's see if we can do one more object because I'm crazy that way. Any ideas? Daryl, what would you like to do? Not an acceptable answer.
Oh, I don't know.
All right, let's take a look here.
You're in Como, 4565 is the first one comes to mind. I know we just looked at that the other night.
Yeah, let's see what's over here. Okay, we looked over there.
Kenneth Benedict's still up. Try the Whirlpool.
Well, let's see where it is. Okay.
I don't know. The Big Dipper's getting over into the western sky now, and
Yeah, I don't know if I want to send the scope over there, but we'll see. Yeah, that's pretty far over there. Actually, we're not that far away.
yeah.
Let's check out. Alright, well, we could probably do this. It's very close to where we are. So let's try it. Alright, here we go. There we go. There it is, right there. Okay, let's go down. And then we will check it out. The Whirlpool Galaxy is really quite an amazing galaxy due to the fact that it's a galaxy in collision. You know, the main galaxy is here, and then this second object is another galaxy that's actually plunging through it. And the disk of the galaxy is warped. If you look at it from the front, it looks like this, right? But from the side, it's going to look like this. this galaxy is warped, so it has a warped disk pointing down at the galaxy that went through it. It's really quite something. So we're guiding right now, so I'm going to go over here and say 20 seconds on this and go for it. Get out of low light mode, go into our live stack mode, clear our last 4725, and this will be the last object, the bonus object that we took images of for tonight. Izabela says she's afraid of horses, but not of bears. Well, how big are the horses you have there, man? Are they like Clydesdales that can stomp you to death? Wow, there we go. Let's color correct right here. Get our curves all aligned. There we go. Look at that. Really nice. Okay. Let's ride up the curve just before the top, because then we won't lose any data. Now we're going to bring this down the mid-range, and that'll get rid of some of the noise. And look at that. That's beautiful. That's the Whirlpool Galaxy.
That's the A51.
Looks nice. It's called M51. F51 Whirlpool.
It's NGC number.
M51. Oh, I'm sorry. What is the NGC number?
4194, 4195, 5194, 5195.
Going once? Going twice? Let's find out. $51.94.
The satellite is $51.95, if I remember correctly.
Alright, so what we're going to do now is zoom in and check it out for a little bit while we're doing it. Look at that. That's pretty. You see these spiral arms here, and you can notice this point right here. Okay? This point is a gravitational protrusion caused by the satellite galaxy as it went through. It's pulling the stars toward it, but it went past it and down through it, so it was pulling it, and then it went and dropped and pulled the disk down. So the disk has a little bit of a downward warp at this end, at least from the studies that I've seen. So that's why this spiral arm is sort of distended, because it's gravitationally attracting or being attracted by this mass. And over here is this is it's probably this galaxy's star is being shredded by this bigger galaxy here. And there's all kinds of other stars out here. If we were to just pump up the brightness here, you can start to see there's all kinds of other haze out here. And those are all stars that are from one or the other galaxies, probably the satellite. You know, and let's do one other enhancement we haven't tried tonight. Let's add an unsharp mask to sharpen this up. And now you can start to see more detail in these spiral arms. Okay. Very nice.
Yeah. I've said before, a spiral galaxy on its own is pretty uniform. A perfect spiral, if you put a line anywhere through the galaxy's center, dividing the galaxy in two, one side should look like the other side. And because so often they're not like that, like we see here with M51, that is a sure sign of a being distorted by a gravitational interaction.
Yeah. So let's say what Darryl was saying. So if we put a line through the galaxy right here, okay, what you see here should be symmetrical up to here, but it's not. This is pointy, and so it's not symmetric on either side. It's also true that it's not symmetric on another line, and that is on this line through the center. You'll notice this arm has been distorted and pulled, I believe, by this satellite galaxy, and you can see it best when you put a line through this. Right, this side has nice long swooping arms. This arm here gets dragged and pulled. See what I'm saying? You don't see that same kind of thing here. These are out and they're billowing out. But here in this side of the galaxy, they're being compressed and yanked by the gravity here. And then this is, you know, the remnants, I think, of this galaxy. There's lots of dust in here, lots of gas. And so the other thing it's thought that this, at least maybe this spiral arm itself, was generated by the galaxy passing through this galaxy. It seems very possible. Okay. So there we go. Just thought you'd like to see that. Okay, we've got 15 shots here for Measure 51, the Whirlpool Galaxy. We're going to save it and let it go a little longer. And why am I letting it go longer? Because we're making an image sandwich. We take these pictures and we stack them on top of each other, making a stack. And we keep track of what we're stacking because these are the images we're stacking. Okay, so we've stacked all these images so far. How many is that? That's 16. Okay, because it says so right here, right there. Right. And so that's pretty good. That tells us in the green, that tells us that the guiding is actually quite good. And so this shot is going to be as crisp and clear as it can be because of the fact that we have this very, very low number. So the guiding error is exceedingly low right now. All right, let's zoom in a little more. Now that we've got this many, we should be able to really come in a little bit more now.
I meant to say earlier when you showed your full width half maximum there, it looked like a night of pretty good seeing tonight.
Yeah, it looks nice. We still see some modeling here. That's actually from the noise at 200 gain. If I had this down to a 100, that's what this camera is best at seeing, but we wouldn't see as much detail. So I go to 200 and then remove a lot of the noise after the fact. So where it wants to be in terms of processing is right here. Watch how bright this is. That's really bright, but you can see now all this additional stuff. You see some dark dust in here. That's in here. You see dust here. You see a very sharp line actually of dust that's been pulled in that direction. That's pretty cool. And we'll pull this back a little bit. There we go.
Turn on that other enhancement you acquired recently.
I have the color is on and unsharp
okay.
mask. Yeah, if we turn it off, okay, and watch what we get. See, that has all the noise.
Yeah, never mind.
We'll get rid of it. Instantly better. Yeah. Yeah, this noise, we can remove this noise. We get rid of that. Okay, beautiful Whirlpool Galaxy. Back out a little more. Excellent. Okay. Let's go right to our peak and let's see if we can blacken the sky here as much as possible. And then wind us out of here a little bit, which will reduce noise, show us more of the galaxy's interior. Look at all this beautiful dark dust in here. Dark lanes are showing very nicely tonight, in spite of the moon.
Yeah.
Yeah, it looks good. Beautiful, beautiful, beautiful. Alright, and I'll also do the annotation. This is not our galaxy. Oh, that's the previous one. So we're going to get the new one here in a moment. It's doing the analysis right now. And you'll see it. There you go. So NGC 5195 is what it claims this is, but I thought you said it was 5194. Oh no, 5194 is the main Whirlpool.
Yes.
Yeah. Well, you'll notice we have IC 4278. IC stands for Index Catalog. IC 4277 and 4282. And those are all galaxies. In fact, in this one view, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 galaxies in this view. And to see them all, I think we have to zoom out a little bit. Yeah. Look at that. Isn't that crazy?
Busy.
It's a busy location. So we have 4284, 4263, 4257 is interesting. It's a very, very small galaxy, but it's not. It's actually not listed as a galaxy. It's listed as other, and I don't know why. Maybe it's an active galaxy. Not sure. Well, there we are. So we'll save the annotation as it is, and then we will call it quits for tonight. Hope you guys enjoyed this. There we go. Now we'll get rid of the annotation, and we'll save this as well. Save exactly as seen. One more zoom in for the night's sake. Wow. Even with the moon, that looks pretty good. Move this way out. Drop some of that noise. We can really reduce a lot of this brightness in the core by dropping this way down. And look at now, you can actually see the blue stars. Look at how sharp that is. The blue stars and that gorgeous dark lane inside of here, the dark dust. You can see the blue colors, see very clearly the blue colors of star formation that occurred in there. That's really nice. I'll save it.
Go to bed, Mark.
I'll save it exactly as seen. Are you saying you want to go to bed? Daryl has to go to bed. Okay. All right, guys. Well, thank you guys for joining us tonight. I really enjoyed your company, and so did Daryl. Although he's half asleep right now, I think. At least I am, but that's okay. I get going and it's hard to stop. All right. All right, guys. Well, hopefully you'll have a good night, and we will talk next time we stream. So you guys keep looking up when you go outside, and I will talk to you the next time on Skyter Livestream. Thank you all for coming. Good night.
Good night, everybody.